Begin. So unit 8, wave motion and sound. So let me just begin. So first of all, let's talk about wave propagation. What does wave propagation mean? Before that, let's define what are waves. So waves are a series of vibrations that travel through a medium, through a material. It's called a wave. Okay. So all waves transfer energy from one place to another. Like light waves traveling out from a light bulb transfer energy from the bulb to your eye, right? And sound waves travel sound energy from, like, I'm speaking from my mouth to your ear. So sound waves carry energy. So all waves carry energy, basically. Okay. So when a wave passes through the material, the particles in the medium simply vibrate. So that form the wave. Okay. Due to vibration, we are going to hear the sound. But the particles always move back and forth past their equilibrium position. They always move back and forth. Don't forget that. It's important. So if you plot a graph like this, you're going to see that the waves are going to be propagate like this. Okay? They are going to propagate like this. This is their equilibrium position. When they reach here, it's going to be like they're going to change their character. Okay? So as you see, they transfer the energy from one place to another. As you see over here, they transfer energy from A to B. So this is how wave transfer energy from one place to another one. So wave pulse and continuous waves. So where wave pulse, there is going to be no repetition of vibration. What does this mean? When you send a wave, for example, it's going to be only one. There is not going to be repetition of the wave. So the wave is going to be just one wave and it's going to move like this. We call this wave pulse. What about continuous wave? For the continuous wave, there is going to be more than one wave repetition. Okay, as you see, there are more than one repetition. When you, like, let's say it's a rope in your hand and you just wave the rope and you're going to see the waves over here. Okay, so we call these waves continuous waves. Okay, these are the continuous waves, and these are the this is the wave pulse. There is only one wave over here. Okay, let's continue. So what about there are two types of the waves. One of them is longitudinal and the other one is transverse wave. So first of all, let's look at for transverse waves. What does transverse waves mean? Transverse waves means where the vibration perpendicular to the direction of the wave motion. What does this mean? As you see, the wave motion is like this, and the vibration, as you see, they are 90 degrees to the direction of the wave. They are 90 degrees. So they are perpendicular to the direction of the waves. What about example for the transverse waves? There are many ways that we can give example. When you look at the electromagnetic spectrum in section 8.2 in your book, you're going to see it. Like all the waves in the electromagnetic spectrum are transverse waves, like light, microwaves, radio waves, X-rays, gamma rays. They're all called transverse waves. Okay, S waves is one another example. Waves on a string, and the waves on the surface of water that you see, the surface of deep water, those waves are called transverse waves. Okay, so all transverse waves consist of a crest, means peaks, and throws. Okay, throws. These are the peak and valleys. Peak we call crest, and the valleys we call it throws. Okay, the valleys. The all transverse waves. Whenever you see waves like this, they are called transverse waves. So what about longitudinal waves? This time the vibration will be parallel to the direction of the motion. What does this mean? It means this. As you see, this is a waves. This is a wave over here. It's moving from right to left. Okay. And as you see, the vibration, it is going to be parallel to the wave. The wave is going like this, as you see, and the direction of the vibration, it is parallel to the wave, as you see over here. It's parallel, the vibration. Okay. So we call this kind of waves longitudinal waves. So what are some examples? Let's give an example. Sound waves, pressure waves, waves forward and backwards through a spring, P waves in earthquake. There are P and S waves in the earthquake. So P waves are P waves are in longitudinal, S waves are transverse waves. Don't forget that, okay? So when longitudinal waves travel through a material, the particles bunch up, then move further apart, okay? They first come together and then they separate. So what does this mean? It means they in one part there is compression, in other part there is refractions, okay? Let me show you here on the, yeah, here as you see, the part which they are apart from each other, we call it rarefaction, okay? The part which they come close to each other, they bunch up or they come together, is called compression, okay? They compress, we compress them. When they are compressed, it's called compression. When they get away from each other, it's called rarefaction, okay? So if the longitudinal wave traveling through a gas, there is going to be compression and the separation part. So the compression part is going to be due to higher pressure, and the rarefaction part, it will be due to lower pressure. For example, here, as you see, that means here there is high pressure, okay? That's why they compress. And here, as you see, the waves are away from each other. That means there is lower pressure, this part, okay? High pressure part, there is going to be compression. Low pressure part, there is going to be rarefaction. So mechanical waves, we talk about electromagnetic waves. Let's talk about some mechanical waves. So what are the characteristics of mechanical waves? First of all, they have speed, they have frequency, and they have amplitude. What does amplitude mean? It's a maximum displacement from the equilibrium position. I'm going to show you here. This part is called amplitude, okay? The maximum position, the maximum displacement from, this is equilibrium position, this part, and from here to here is called amplitude, okay? Amplitude. It is maximum height of the wave. We call it amplitude. It has a wavelength. Wavelength, we are going to use lambda. This is a Greek letter, lambda. We used to define wavelength. So it is minimum distance between 2 points of adjacent waves. Here, let's go back here, between these 2 points, between here and here, it's called, let me just take a pen. So from here to here, this is called wavelength, okay? That is wavelength. So we call it wavelength. Here, and there is an example, as you see. So wavelength, okay? So then let's continue to frequency. Frequency means like the number of complete waves passing a given point per second. The SI unit of frequency is hertz. The SI unit of frequency, or you can say 1/2. Okay, 1/2 or hertz are the SI unit of frequency. So the period, on the other hand, is going to be the time taken for one complete wave to pass a point. We call it a period. For example, here there is a complete wave, right? In these two, between these two amplitude, we call it a period. The SI unit of period is second. So in order to find the period, we are going to use 1/2 or 1/frequency. We are going to use the formula 1/frequency to get the period of a wave. Okay. So the time period is reciprocal to the frequency. What does this mean? It means when you find the frequency, you're going to use 1/period, or when you find the period, you're going to use 1/frequency. Okay. So the second equation is so important. Why? Because it relates to wave speed, frequency, and wavelength. Here, this equation is very important. To find the wave speed, we are going to use the frequency times wavelength. When we put them in the like we used to show wave speed with letter V, and the frequency with F, and the wavelength with lambda, Greek letter. We are going to use this formula to find the speed of the wave, or frequency of the wave, or the wavelength of the wave. Anyway, we can find it. Okay. So what are the differences between mechanical and electromagnetic waves? So all mechanical waves, don't forget that, require a medium, require a material to travel through. Okay. They include sound waves, water waves, and seismic waves. But for electromagnetic waves, they do not need any medium. They can travel through vacuum, they can travel everywhere. Okay, and there are no particle vibrations inside that medium. Okay, there is no vibration inside of the medium when you put electromagnetic waves inside the medium. They don't need any vibration in order to travel. Okay, so they can travel through air, through vacuum, but mechanical waves cannot travel through vacuum. They only travel through a medium, through a material. Okay, so what are some examples of mechanical waves? So let's give some example for mechanical waves. So first of all, there are many examples for the mechanical waves. We are going to learn about two of them: water waves and seismic waves. So water waves, let's begin with the water waves. What does water waves stand for? So water waves travel through surface of the water. Okay, there are transverse waves, but there is often a slight drift in the direction of the wave motion. So they are not perfect transverse waves. Okay, they are not perfect transverse waves. We call them transverse waves, but you cannot say that they are like electromagnetic waves, like they are perfect transverse waves. They are not, because of the slight drift in the surface of the direction of the wave motion. So the speed of water depends on the depth of the water. What does this mean? That means when the depth increases, the speed will increase as well. Okay, the depth increase, so the wave speed will increase as well. So in deep water, waves can travel very fast, in 100 km per hour. Okay, in hundreds km per hour, they can travel in deep water. The depth and the speed of wave are directly proportional. The second one, there are seismic waves. These waves are produced by earthquakes. They can travel from the focus in all directions throughout the earth. Okay, they can travel anywhere. There are three types of the seismic waves: the L waves, P waves, and S waves. L waves are complex types of rolling wave. They can travel along the surface of the earth and cause most damage to the buildings. When there is too much damage after earthquake, this is because of the L waves. Okay. The second one, P waves. These are the premier or pressure waves. These are the longitudinal seismic wave that can travel through the solid and liquid parts of the Earth's structure. They can travel through the water or through the rock. They can travel P waves. The third one, S waves. These types of waves, they are transverse seismic waves. They can travel through the solid part, only solid part. Okay, only solid part. They can travel. That means only through the earth they can travel. They cannot travel through the seas or oceans. Okay, these are the S waves. We call it seismic waves. What about the wave equation? Let's talk about the wave equation that we learned about it actually. The speed of the wave is equal to frequency times lambda. Frequency F stands for frequency here, and lambda stands for the wavelength. So the SI unit of speed is meter per second, the frequency hertz, and the wavelength we find in meter. So there is an example here. A water wave travels at a speed of 80 meters per second with a wavelength of 20 meters. So calculate the time period of the wave. So in order to find the period, what we have to do, first of all, we are going to find the frequency in the formula, okay? When we find the frequency, we can find the period by using 1 over frequency equal 1 over period. We can find the period of the wave. So first of all, let's find the frequency. So frequency, just a second. So to find the frequency, we are going to use this formula: frequency equal speed of wave over the length of the wave. When you divide it, 80 over 20, 80 is the speed, 20 is the length of the wave. We are going to find 4 hertz, the frequency of the wave. So second of all, to find the period, we are going to use this formula: 1 over frequency equal to period. So it's going to be 1 over 4. This is 4, we find it. So then the period will be 0.25 seconds. This is going to be the period that we are looking for. Okay, so this is how we find the period. All right, what are the wave behaviors? Some wave behaviors, let's talk about it. So the waves can exhibit reflection, refraction, diffraction, and interference. Okay, these are the some common words that we are going to learn about the waves. The first one is the reflection. Reflection means like when a wave reaches a fixed surface, it is going to be reflected on that surface. Okay, this is the reflection. For example, when you send light rays to the mirror, they are going to bounce back. Okay, this is called reflection. So the ripples spread out as circles from the source. What does this mean? For example, when you send the light rays to a barrier, they are going to be reflected like this. Okay. So after they reflected, they are going to form a barrier. They are still circular waves. Okay. And they continue spread out by they traveling opposite direction. As you see, they are going to move in opposite direction. One of them goes like this, the other one goes on the other direction. So this is called reflection, the first part, reflection. For example, when you like when you throw a rock inside of water, you are going to see this reflection. The waves are going to occur and they're going to spread all around. Okay. So what about refraction? Refraction means like when the light ray change its place, change its medium. For example, from when you put a pen inside of a glass of water, you are going to see like the pen is like broken. It's going to be seen like that on the outside, but actually the pen is still the same pen. Okay, that means over there, since the material changed its like medium from air to water, there is going to refraction will happen there. Okay, it is going to bend towards the like the normal. Next year, when we learn about optics, we are going to learn more like details over there. But this is just an introduction part. So again, when an object change its medium, change its like place from one place to another one, when it enters, that means the object will face refraction. Okay, it is going to face refraction. As you see over here, there are incoming ripples. When they entered another medium, they got closer to each other. Why? That means here the density is higher than this part. This is the reason. Okay, this is the reason. Okay. Already we defined already reflection and refraction. What about diffraction? So diffraction occurs when a wave passes the edge of an obstacle, as you see over here. When it passes the edge of an obstacle, the diffraction will happen. Okay. So the ripples they spread out into the space beyond the gap. As you see, they are spreading up over here and here. So the narrow gap has more effect than the wide one. There is more spreading out with the narrower gap. Okay, as you see the gaps here and here, you can see them. The narrow gap has more effect. Don't forget that. Okay. So the effect of diffraction is the greatest when the width of the gap is the same as the wavelength of the waves. So a bigger gap has less effect. Okay, a bigger gap will have a less effect of the diffraction. So what about interference? Constructive and destructive interference. There are two types of interference. To observe interference, we need two sets of waves. If the two waves are in phase, in step, we call it, with each other, they combine and make a bigger waves. Okay, as you see over here, when they waves travel, two waves are traveled in the same direction, and when they interfere, when they meet each other, they're going to do constructive interference. Okay, and they're gonna be at the end a bigger wave. You can try this. Like you can put water inside of a bucket and you can try it there. Okay, you can put something inside of water and you can like produce two waves, and when the waves meet, their amplitude will double. Okay, and they're going to be like this. We call this constructive interference. What about destructive interference? Destructive interference means like when waves cancel out each other. Let's say there are two waves, they act in opposite direction, as you see over here. Like one of them goes a green color, the other one goes with the blue color. And if their amplitude are the same, they're going to cancel out each other. At the end, they're going to have this wave. Okay. There is not going to be wave at the end. So we call this destructive interference. All right.